To study motion, we have to make a moving body leave traces after short and equal periods of time. If a body is moving with a constant speed and covers equal amount of space during any equal time periods, this type of motion is called uniform. If the speed changes and the chunks of space covered turn out to be different, this type of motion is called non-uniform. This trolley can be pushed by a built-in spring. There is a screen installed onto the trolley. The motion detector sends an ultrasound signal, which is reflected by the screen and comes back. The motion detector determines the distance to the trolley by the time the ultrasound signal needs to go there and back. We'll be sending the signal 10 times a second. We send the trolley moving. The diagram on the screen shows us the dependence of distance on time. Equal amount of space is covered in equal periods of time, which is why the movement of the trolley may be considered uniform. The trolley has covered 42 centimeters in 1 second, so its speed equaled 42 centimeters per second. Let us equip the trolley with 2 springs and stretch the springs to engagement stops. This type of motion is of course non-uniform because the speed of the trolley increases and decreases in turn. Moreover, it moves in different directions. Let us have a look at what the diagram of its motion is going to look like. We set the motion detector, push the trolley and see that the motion diagram looks like sea waves. The trolley bounces off the balanced position in one direction, then in another, with the amplitude gradually decreasing. A computer can do the calculations for the speed diagram using the distance diagram. Here it is. It is remarkably similar to the distance diagram in its shape. However, when the equilibrium deviation was at its maximum, the speed equaled 0. And when the deviation was 0, the speed was at its maximum. Now we're going to make use of an amazing phenomenon. Let's take a strong neodymium magnet and an aluminium tube. The magnet is not attracted by aluminium. Now we're going to throw the magnet into the tube. Is it stuck inside? No, it has fallen out eventually. The tube slows down the moving magnet because eddy current flows appear in it. To see the magnet moving inside the tube, we stick to it a straw with a tennis ball at its end. We push the magnet into the tube and let go of the straw. Look how slowly and smoothly the ball is going down. We're going to use this phenomenon to make a magnet break for our trolley. A thread is tied to the trolley. A magnet is attached to the other end of the thread. We put the thread over the block and put the magnet inside the tube. Let's start the trolley. We'll do that again and record the motion diagram. Here the trolley is moving forward fast and then is gradually slowing down, whereas here it is moving backwards slowly and smoothly.